But this is what I figured out. If I record using Snagit, and you can see I actually am recording here, it records the screen so that when I pull up the websites that we were playing with, it'll then record it. Because when you looked at the videos, it didn't have the websites in it, did it? Because it was just recording from the camera. So there's a difference between recording the screen and recording the camera. See all these things that we're learning? Here's your Unit 3 reference sheet. So what I would like you to do with your group mates is I would like you to go through it, and you have highlighters and colored pencils. Take a pen or pencil to it, and I want you to annotate it because theoretically you know everything on it. How about that? Theoretically, everything that's on this sheet is already living inside your brain. So I would like you and your group mates to take a pen or a pencil, a highlighter, marker, colored pencil, and go through and talk about what you already know. And your mark is set, go. All right, so if I were an applied calculus student and I was interacting with this is kind of cool to get after the fact because I can see how much it is I have and have not learned. It's so important for you to know the difference between the average rate of change and the instantaneous rate of change. That's the whole reason why we're doing this. So this average rate of change is really nothing new. This is my change in my y compared to my change in x, which since Algebra 1 days, I've called slope. So in my Algebra 1 days, I did y2 minus y1 over x2 minus x1. And it doesn't matter where I find my average rate of change. When I take the distance between the x's and the distance between the y's and I compare them, then I can go ahead and see each of these average rate of changes. The problem is with this story is it works great in the linear scenario, but that's so Algebra 1, and we're so far beyond that. So now we've got all these curves, so we have to find a better way to understand rates of change on those curves. So with the derivative is I end up closing the gaps between my x's, and with each next line that I get closer and closer, my estimate of my rate of change becomes better and better and better and better until I'm dealing with really a tangent line. So then you're like, okay, well, if the tangent touches the graph one place, how do I get my 2 points to put into this? And that's the big question. That's what they figured out by coming up with the derivative. So this problem, this very problem of I want to try to get closer and closer and closer and closer and closer to what's happening at that exact point and be as accurate as I can. And we put you through that with talking about the COVID, flattening the curve, number of cases at any given point. We put you through that with the brake exploration. We put you through that with, what was it? Was it Aaron riding her bicycle? So each of those instances of finding those rate of changes, what we wanted to do was to make this difference here between my x's as small as possible so that this was an accurate representation of that change. Okay, so the derivative of any given point is the instantaneous rate of change. And then what ends up happening is this slope formula, that's where these d's come from, because the derivative is where that change in the quantities is so very, very, very small. So that's what that D stands for. So when we were doing average rates of change in Algebra 1, Algebra 2, and pre-calc, which is actually Algebra 3, that change in y over change in x, that d becomes that very, 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 very small delta. And the d makes sense if you know that this is the delta symbol, which means change. So when you hear the Greek letter delta is a triangle and that means change, then it all starts to make a little bit more sense. All right, that's why we're doing what we're doing. Okay, here's the next tricky part. Every time we ask you for the derivative, we're asking you for it in a different phrase, which you're like, why not just use the same thing? Like, well, that would be too easy. We want to make sure that you are fluid in all these different synonyms. So if you have a function, y is equal to the function of x, all of these are representing the derivative. The only thing I would add to that is if somebody asks you to find the slope of the tangent line for a function. And this is an interesting conversation. We need to talk about when that request is made of you. Number one, for the function. And number two, if someone's asking you at a specific value. So if you're given x is equal to some value, we're looking for that actual rate of change. When we're having a function, I'm asking you for some kind of equation with an x in it that tells me what that slope of the tangent line is. So if I want that slope of the tangent line for that equation, if it's got a variable in it, then I need to know what x value you're interested in to get more specific. You'll tell me about that value as we go. All right, coming on to the back. Our secant line represents that average rate of change over this interval. And what we learn is this interval, we're going to start calling h. And that is the same as my change in my x's. Because what I'm looking at is how many points are in between each of those things. And when we're finding that value, that slope of the tangent line, we're able to talk about it, and then that's when we go to talking about the limit as h approaches 0. So in order to figure that out, we ended up using the limit to say, okay, I see this tangent line is this big, but what if I wanted to squeeze it down so the difference between my x's, and I want to know what that value is as my h gets smaller and smaller and smaller and smaller and smaller, as the difference between those points gets smaller and smaller and smaller. Our limit definition of the derivative helped us do that. So when I take the limit as h approaches 0, I'm taking my function that was original and I'm putting it through the slope function with f of, with x plus h minus x. This is the same as my change in my output compared to my change in my input. We simplify that, and that's where I get the limit as h approaches 0 of f of x plus h. That's my second point. F of x is my first point. And all I'm left with is these h's once these x's cancel out. So that limit definition of the derivative will work every single time. And you're like, no, thank you. That's really sweet. I appreciate you offering, but I'm going to say no, thank you. Because that's like asking me to go buy a bolt of fabric and sew my own clothes every day. Like there's faster ways of doing it. So some people might like to sew, good for you. But at the end of the day, I'd like to be able to reach into my drawer and pull out a shirt, put it on and go to school, right? So it's important to understand where this comes from. But then we end up being able to shortening it to some of these basic properties and understandings. And what this shows us here was our power rule. Anytime that you want to find the derivative, of a value, you can go ahead and do this following thing and give yourself an example. If y is equal to, give yourself just something really simple, x to the 12th power, and tell yourself that the derivative is going to be 12x to the 11th. When I'm taking the derivative of that, if I wanted to take the time to put it through this limit definition, I could, but I'm not going to bother, because after doing it so many times, mathematicians found this pattern, because your equation of your derivative is going to be 1 power level less than your equation. And that coefficient turns out to be what's in the front. All right. So then all these other rules kind of fall into place. When we talk about the derivative of a constant, tell yourself that this C stands for a constant. And remind yourself that E and pi are our two sneaky constants. And make sure you know that the derivative of a constant is 0. And give yourself a little sketch, because anytime I have a constant, you know that that line is a horizontal line. And we talked about a horizontal line with a slope of 0 and a y only. So of course my slope is equal to 0. So if I'm looking for the slope of a tangent line of a constant, that slope is 0. That's why the derivative of a constant is equal to 0. This one is really simple, because this is the one that reminds you that you're just going to take the derivative of each thing and add or subtract it as you go down the line. These are the easy ones. This one is also fairly easy, because this is where just this coefficient is out in front, and it answers how many of these things do you have. So it just continues. So give yourself an example. If I have 4x to the thirds, that means I'm going to have 4 of those derivatives. And that's what leads you to 12x squared. So if my function is equal to that, my derivative, and this needs to have 1 tick, not 2. So we don't often break it down into see this 4. We just do 3 times 4 is 12, take that down a power. But if you want to know why that is the way it is, here's the thing. If you're worried about remembering 152 individual ideas, it's a lot. If you're thinking about and understanding the concepts, then they make sense to you, and that's not something you necessarily have to remember, because you understand it. So to me, those are all the easy ones. Are you with me on that? Okay. Your product rule and your quotient rule are going to be ones that you have to have memorized. This is the one that we sing a silly song to. And I actually, when I sing it, my F prime of G is where I do my low D high minus high D low, square the bottom, and away we go. So I tend to always start with the low. But the commutative property of multiplication says whatever order you do these in, you're fine. Are you okay with that? So I had Miss R in here the other day, and I made a poster for our Unit 3 that goes up on our wall. And she says, I don't like the way you did this here. And I don't like the way you did this here. And I said, well, this is my low D high minus high D low, square the bottom, away you go. She's like, these two should always match. She says, that way you remember the only difference between your product and your quotient rule is that your product is where you're adding and your quotient is where you're subtracting. And I said, I disagree. I said, I think that they need to do it however it makes sense to them. And as long as that's not confusing for you, when you do your first term times the derivative of your second plus your second term times the derivative of your first, as long as you remember each term gets their shot of having a derivative times, it's the derivative of one times the other. The derivative of one times the other. All of this multiplication and all this addition is commutative, so it doesn't matter what order you do it in. Does that make sense to you? So if you're a person who likes the order and you'd like to see it, here it is written for you in that order that's common. So maybe that structure will help you. If you like to sing the song, you can switch this around to G times F prime plus F times G prime. You can do whatever you want. I got to tell you the truth, when I do it, a lot of times I look at my things and see which one's easier, and I start with that derivative because that makes me feel good that I can get something under my belt. Does that help a little bit? Okay. Chain rule we're going to do next unit. We moved it to the next unit. So if you're worried about chain rule, that's coming next. All right, here was the part that we were missing. We were fine up until last class. So this is the part that we were missing. And I got to tell you something. I'm not going to waste my time memorizing this because I don't need it. That just makes sense to me. If y is equal to x, y prime is going to be equal to this 1x to the 0. Anything to the 0 power is equal to 1. And that's where I get 1. I can logic that on myself. I don't need one more thing that I have to carry around in my brain. This one is so cool just because E is one of the most beautiful kinds of ideas and concepts. And if you're curious about the difference between these, this actually continues on with the natural log of E, but everybody knows the natural log of E is 1. So that's why we don't bother doing that one. So you can kind of see the symmetry that happens between these. So if you're going to memorize one, this is the one that you need to memorize. The derivative of anything to a power, where my variable is in the exponent, is going to be that thing times the natural log of that thing. So if you memorize this one, you've got this one in the bag too. Somebody said to me yesterday, I thought E was a constant. Yeah, it is a constant, except for now it's a constant to a power, so we care about that x. In the same vein, if you're going to memorize anything, this is the one that you would memorize, because when you're taking the derivative of a log, it's 1 over the argument times the natural log of the base. And then, of course, if we can add whatever's going on here, it's 1 over the argument times the natural log of the base. Well, it's base E. The natural log of E is 1. So that's why this part is not in that one. The sine and cosine ones, we looked at those graphs, and I'll pull them back up so we can look at them. They need to be memorized. Miss Holdaway and I decided we were going to give you these on the board. So they're ones that you need to know how to substitute in. But if we want you memorizing, you're going to have to be responsible for knowing all the ones before this, but these are the ones that we'll put on the board on the day of the test. A little bit less memorizing for you. Sound okay? Okay. In your Schoology website, underneath your assignments, I did put the derivative websites in there, which I thought was pretty cool. This one is kind of cool because you practice raising and lowering the value of the derivative. And I want you to spend some time trying to look at each of those tangent lines, recognizing whether it's a positive value, recognizing, and it's the yellow lines that you move, the green lines, you can go back, the green dots you can go back and manipulate, because those will change the functions. I'll show you in a minute. When it asks, would you like to check your work? This is pretty cool, and I want to make sure, how can I get this whole thing in here? Okay. So when you want to check your work, it says slide me slowly. I want you to watch what ends up happening. So it takes each of these differences, and then it takes each of these, and what it does is it shows you the slope of the tangent lines. So I did pretty okay with each of these. It shows you the rise and the run, and it shows you the equation of the derivative. I think that's kind of cool. And what's fun is you can also, before you do that, so let me reset. So, and again, I wonder why this, okay. You can go ahead and change your function to whatever you want. So if I look at that function, I can go ahead and change each of my tangent lines to try to understand. Oops, I didn't want to change that. Can't see it. Where's my other yellow dot? There he is, way up there. And then you can take your pencil and you can trace what you see happening by your dots. And then you can check your work. And slide me slowly. And you can see my line was a little off here. Anyway, I thought that was cool. Derivative website 1, play with that. Your next conversation, and this is the one where we had a good time playing with sine and cosine. So come down here, derivative, our tracker website. You want to go ahead and you can change, and this is where we went in and we changed this to the sine of x. And then when you can see then there's that cosine graph. The derivative of the sine of x is the cosine. And you can play with each of those. So each of those websites is in your Schoology, and you can type in any equation that you want in either one of them, and that will help. All right, enough of me talking. What I'd like you to do is take out your homework for 3-4, and we started these together, and what I would like you to do is talk to your group mates about what you got for the other ones. Go ahead and chat. Okay, so we're okay at 1, 2, 3, 4, and 5. Didn't we do 6 together? No. Okay, so do you see how it's a product? X times the cotangent of x, right? So I need to use my product rule. So here's my first term. The derivative of the cotangent of x, the derivative of the cotangent of x is the opposite of cosecant squared x. So that's what goes in there, plus the derivative of x is 1 times cotangent of x. Now, you have a test next class. So here's what we need to know. I'm going to say this loud and clearly. Make sure Adrienne hears this when she comes back. That's good enough for an answer for me. The test is about the calculus, not the algebra. So in our future units, we're going to be simplifying and coming up with an answer. That's the purpose of calculus. Answer these really hard problems. Use math to help you figure it out. But we need to make sure that we know how to do the math. So if you put this down as an answer, you get full credit because you applied the calculus. Are you with me? But we still need to be able to practice doing the algebra because someday somebody's going to want an answer from us. Okay. So this says at pi over 6. So when I'm looking at each of these values, when I look at my unit circle and I think about where pi over 6 is, I know that I have root 3 over 2 as an x value and 1/2 as a y value. So there's my cosine and sine. Everybody okay with that? For pi over 6. So now it's my job to fill in what I have. So the derivative at pi over 6. And this becomes an important point. You're not solving for just any value. You're solving for when the derivative, or when the slope of the tangent line is at pi over 6. So that's going to be equal to, instead of x, I'm writing pi over 6. Now let's talk about cosecant. Cosecant is friends with sine. So I want the opposite of 1 over my sine value squared. So my sine value is 1/2. So 1/2 goes in there. You okay with that? So that's going to take care of the cosecant squared of pi over 6. Plus, I don't need to deal with this 1. So now I have to deal with my cotangent of pi over 6. My cotangent of pi over 6 is root 3 over 2 over 1/2. Because cotangent is cosine over sine. Is everyone with me so far? So my derivative at pi over 6 is equal to my input value, pi over 6, times, this is going to be the opposite of this value squared. 1 divided by 1/2 is the same as 1 times 2. We're all okay with that? So 2 squared is 4, so that's -4. Do you want to see that written out? Say yes if you do. Yes. Okay. 1 divided by 1/2 squared. So 1 divided by 1/2 is the same as 1 times the reciprocal squared. So that's how I get 4. And then this negative sign is hanging outside as the opposite. It's not a part of that, so it's the opposite of cosecant squared. So it's the opposite of 4. Does that make sense now? Awesome. So in the same vein, -3/2 divided by 1/2 is the same as, and we'll do that math so you can see it. If I have square root of 3 over 2 divided by 1/2, that's the same as root 3 over 2 divided by 1/2. That's the same as root 3 over 2 times 2 over 1. So that answer is just root 3. So this is going to be plus the square root of 3. So the derivative of pi over 6 of this function is going to be -2/3 pi plus the square root of 3. And that's my final answer. Sound okay? All right. So when we talk about finding the derivative, it looks like a quotient, but because there's 1 up here, we don't have to really worry about doing the quotient, the derivative of the quotient. We can just call this y is equal to 2 times the cosine. Well, why don't we do this? We'll just call it 1/2 times cosine of x to the negative first power. So cosine of x is equal to, you know what, we need to do the quotient. I lied. We don't know how to do this yet. Ready? We have the low d high, derivative of 1 is 0, minus high d low. So we end up with negative 2 sine of x. Square the bottom. And away we go. So y prime is equal to, this zeroes out, and negative becomes positive 2 sine of x over. This becomes 4 cosine squared of x. So my y prime is equal to the sine of x over 2 cosine squared of x. Okay? So this one will help you out if you see it cosecant of x times cosecant of x. That's going to be our product rule. Henry, grab a, we're just going over homework. Y prime, if I go back to my cosecant rule, there it is. So I have my first term times the derivative of my second. And the derivative of my cosecant rule is opposite of cosecant x cotangent x plus my first, derivative of my first, which is the same thing, times my second. Everyone see that that's going to be just 2. This 2 comes out front. And it could have been 2 times cosecant x times negative cosecant x cotangent x. So you could have, instead of doing the product, you could have used the power rule. 2 comes out front, and then here's the derivative. Everybody okay with that? Go ahead, Isabel.
When you said y equals like the first line,
Yeah.
the x outside the thing?
Yeah.
What's that? I just wanted to like.
Nah.
Okay.
There you go. We okay? Theta over the tangent of theta, that's got to be the quotient rule. So r prime of theta, and theta is the same as x. Did you ever notice on your calculator, they have, for your variable button, there's x, t, theta, and n? That's the key for the different variables for the 4 different modes of the calculator. So if you press mode on a calculator, when you put it in, whether it's degree or whether it's radians or, so whether you're doing with probability, that's the different thing. So theta is no different from x. Okay, so we have r prime of theta is equal to, and we can go ahead and do our tangent of theta squared. For some reason, when I do the quotient rule, I just always, when I do the low-d high, high-d low, the square at the bottom and away we go goes at the bottom. Jaden, are you with us? So for some reason, that's always something I like to do first. All right, so low, d high. So pretend this is an x. So then, oops, I wanted to put this in curves. Low and then d high minus high. And then the d of the low, the derivative of the tangent. I keep mixing up my boxes and squares. Derivative of the tangent is secant squared of x. So my derivative of theta is tangent of theta minus my theta value times secant squared of x all over tangent squared of theta. Now, if somebody comes along and says, can you figure out the value of the derivative at any one of those points on the unit circle? The answer is yes. 0, pi, 2 pi, 3 pi over 4, 11 pi over 6, whatever you need, that's what I plug in for my theta. All right. Do you see this as a product? Negative 17x times log base 8 of x. H prime of x is going to be equal to my first product times the derivative of my second. Log base a, 1 over a times 1 over x times the natural log of a. So that's going to be 1 over x, and in that denominator is the natural log of 8. My first times the derivative of my second plus my second log base 8 of x times the derivative of my first. So nobody cares about the order, but you're welcome to try to simplify negative 17 x's over x natural log of 8. Those x's will cancel out. Plus negative 17 times the log base 8 of x. H prime of x is going to be equal to negative 17 over the natural log of 8 plus negative 17 times log base 8 of x. We doing okay? Quotient. Do you recognize this as a limit definition of the derivative? Anybody? Here's our original function here, cosine of pi over 6. Right? So we could go through and do the whole thing, the limit as h approaches 0. Right? The directions say find the derivative of each function. This is already given in the limit definition of a derivative format. What do you think we should do with it? Any thoughts? do you think we should do with it? If I plug h in for 0, I get an indeterminate form. I get 0 over 0. What do I do?
Distribute the cosine to the pi over 6 and the h.
So I'm not sure you can distribute because it's not a coefficient. It's the cosine of that value.
And multiply the top and the bottom.
What do you want to multiply it by?
The numerator. Numerator, like take the numerator and
So find a common denominator. So the cosine of pi over 6 plus h, that's a value. So think about our cosine graph. Looks like this, right? Right? So if I'm finding the cosine, let's say here's x plus h. It's the cosine of this minus the cosine of that. So what I totally want to do is just find the limit of the cosine at pi over 6. I can't stop seeing that I already know what the function is. Anybody with me there? So my original function is equal to the cosine of pi over 6. Didn't we just have the cosine of pi over 6 over here? Isn't that root 3 over 2? So the cosine of pi over 6 is equal to root 3 over 2. The derivative of a constant is
0.
holy trick question. If I'm asked to find the derivative, that's what that's going to end up being, right? If they had given me a theta here, then when I go to find the derivative, it would be the opposite of the sine of theta, right? But once they give me the derivative of that value, that's that value. That's a constant. That's like y is equal to 4. Slope is 0. It's a constant. Cosine of pi over 6 is a value. So, all right. If f of x is equal to this, find the derivative at 0. So first of all, let's find the derivative. F prime of x. Here I have one value. Here I have another value. So I could just use my power rule. The derivative of e to the x is just e to the x. The derivative of the sine of x is the cosine of x. So because of this addition sign, it's just the power rule down the line of the function. I don't have to do any of that fancy power or quotient or product or quotient stuff. So if I want to find the derivative at 0, that's going to be 4 times e to the 0 plus 5 times the cosine of 0. E to the 0 is 1, so we'll call that 4. The cosine of 0, isn't that 1? Right? All right, the limit definition of the derivative is what you already know how to do. So I'm going to stop talking because I've been talking for 44 minutes with mine. And check me if I make any mistakes. You know how that'll happen. So the limit as h approaches 0, it's all over h, and my original function is 1 over 2x, and my next function is 1 over 2 times, careful here, x plus h. Those parentheses are key. So I need to find a common denominator. Each of these has a 2. This needs an x plus h. This needs an x. So my limit as x approaches 0 all over h is equal to x over 2x times x plus h minus x plus h over 2x times x plus h. So then my limit as h approaches 0, and you kind of don't need to write that every time, but you can. X minus h, because I distributed that negative, all over 2x times x plus h, all over h. X minus x is a 0 pair. These h's cancel out, which is why I end up with just -1 over 2x times, and then this h goes to 0, so it's just 2x times x, so 1 over 2x squared. It didn't give me a value. And if you think about this, I just validated my power rule, because if I know that f of x is equal to, I could have called this 1/2 x to the -1, which means f prime of x would then be equal to -1/2, here it is, times x to the 1 less power, which is the same as -1 over 2x squared, which is exactly what I got.
Did you drop the 2 when you did the common denominator?
I did not
So where did it go?
drop the 2 because here's my 2. So this guy's factors are 2 and x plus h. This guy's factors are 2 and x. So 2 was part of the common denominator. And then I needed 1 factor of x plus h and 1 factor of x, because the 2 was already there. We okay? Okay. All right, the limit definition of derivative. So again, if we cheat, are you in the mood to cheat?
Yes.
Stop. 8x to the 1/2 power, right? So what we're hoping down a long and winding road, that we figure out that the derivative is equal to 1/2 times 8 is 4x to the -1/2 power. So we're hoping for an answer of 4 over the square root of x. That's what we're hoping for. Are you ready? Do you want to see it? Yes or no? The limit as h approaches 0 of, here's my h, here's my 8 square root of x plus h, and she did us a favor by not putting a 2 under there. Thank you. Minus 8 square root of x. Everybody okay with that starting? Hey, this is a conjugate one. And in my head, when it takes me so long to write out the conjugate, I tell myself, this is a story of 2 mathies sitting around a table looking at this problem going, let's make up something super cool that's going to solve all of our problems. And they're like, yeah, yeah, yeah. The only way to eliminate a radical is to square it. And let's use the sum difference binomial multiplication pattern to get rid of those middle terms. They were so excited, those mathies were, when they figured this out. Because when I FOIL, my first terms will take care of each other. So 8 times 8, 64, that's outside of the radical, so I have to pay attention to that. Times x plus h, that square root goes away. Are we okay with that? My outer terms are positive of these two multiplied together. My inner terms are negative of these two multiplied together, so they end up being a zero pair. So I don't bother writing them out because it takes up too much time and I don't need to. My last terms are 8 times 8 is 64. Square root of x times the square root of x is x. Positive and negative, give me a negative. Limit as h approaches 0, 64x. Oh, I forgot to multiply the bottom. What? I like that better. Okay, 64x plus 64h minus 64x all over h times 8 times the square root of x plus h plus 8 times the square root of x. My 64x's cancel out. My h's cancel out. And I get 64, and my h goes to 0. 64 over 8 times the square root of x plus 8 times the square root of x. 8 plus 8 is 16, right? Doesn't 16 go into 64 4 times? And it matches. Okay. Yeah. Okay. All right. Yeah.
Last one, on the test, can we leave the square root of x in the denominator?
Yes. So if you need clarification on the test of what you are and are not allowed to leave, by all means, that's fine. But what I really want to make sure you understand is the calculus and the derivative practice that comes. All right, so here's your review packet for the test. Now, we've got a couple activities that we never had time for. So there's 15 minutes-ish, more like 13, left in the class. And I want these last minutes to be a valuable use of your time. So here's the deal. What do you want? Do you want to start on the homework? Do you want to start on the homework together? Do you want to do, I have a Jeopardy game with practice problems where we could all work on them. A partner activity that focuses more on the last time's lesson. That's the one with tangents and cosecants and logs. So I'm willing to do, if you want some sample problems, the Jeopardy game is kind of fun. Oops. Where you get Jeopardy game with some practice. 10 minutes. What do you want? Okay. Whiteboards, or do you want to work on a piece of notebook paper so you have those problems to study from? The problem with whiteboards is when you erase them, they're gone. So why don't you take out a piece of notebook paper if you need to grab one of mine, and we can walk through and do these activities together. Da 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 da. Da 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 da. Dum da dum 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 dum. Okay. So our three contestants are these two groups are going to work together as one. These two groups are going to work together as one. And you two groups are going to work together as one. Everybody okay with that? So you pick a question and a dollar amount. We'll keep track of. Everybody does the work, and then the first person to get the right answer gets the dollars. You okay with that? So we'll let group one go first. Our categories are product, power, and quotient rule, definition of the derivative, exponential, logarithms and trig, differentiability, and continuity. Those are all of our topics that are on our test. Group, what do you pick?
500 for differentiality and continuity.
So you're gonna go deep fast, right?
We got 10 minutes.
Go. For what values of x is a function not differentiable? Everyone's doing the work. First one to buzz in. Go ahead. Grace.
Okay, so there's a whole x plus 2.
I agree. So which value for that?
2.
Two.
Sorry. I didn't understand what you were asking me, sorry.
Okay. So we got a whole at x plus 2 or x minus 2 and x equals negative 2. Is that your final answer? All right. Nope. Anybody else? Go ahead.
X equals negative 4 and 3.
Nope. Why 3? Where does 3 come from?
Oh, it's the vertical, or it's the vertical asymptote.
It's the vertical asymptote. So
I get like half of it.
you know what? I will give you 200. I will give you 200. I get to be my own version of Alex Trebek today. Yeah, don't forget about the vertical asymptote, right? Right? All right, middle group, what would you like to do next?
Could we do 400 for the same time?
Create a graph that is discontinuous. You can draw on a piece of paper. Only at x is equal to -4. And 2 is not differentiable. At x is equal to -4, 2, and 4. Got it? Draw it on the board. Go get a marker, draw it on the board. All right, so let's see what he's got. He's got at x is equal to -4, it's discontinuous. And at 2. Is it supposed to be discontinuous at 2?
Oh, 2, I didn't, there's a hole there, imagine.
I read that too. So so this has gotta be a whole discontinuous and is not differentiable at -4, 2, and here's our cusp. I'll buy that. So I'm gonna take $100 off. So it's 300. You're up to 500. All right. Group. Why is it not clicking for me? I'm clicking everywhere. There it goes. Yeah, because it was supposed to be a graph. All right. Same group picks.
Oh, be again?
Pick it. Go ahead, pick.
Definition of a derivative 500.
You know it's going to be a long one.
Oh my god, yeah. X equals.
Definition of derivative. Find the value of the limits when x is equal to 5. So if we see this, does that help us validate that, right? No, because you got me thinking too, right? So it's hard to tell because we're right? No, it's impossible. And then what it's happening is, when you what kind of function is it? So you go from see, hold on. You got it. Good job, Steven. What did you do?
I listened to you when you were talking
Oh. What did I say?
that we can see the original function.
Yeah, so that's that was this one, right? You can see this original function, right? There's my original function. So if I took my derivative of that, isn't it 9 minus 100x? Right? No, 20. Right? So it's 9 minus 20x. So when you put 5 into that, and that goes back to what Kaylee and I were talking about before. It's a great question. Thanks for picking. All right, you guys got $500. It's a tie game.
We haven't gone to 0.
Oh. Hey, everybody, do your homework. Thanks for playing.